morning. We have been discussing the behavior of microscopic particles like electrons, and we considered a situation where we had an electron beam incident on two slits, and we were looking at the pattern of the arrival of the electrons at a distant screen. And what we found was that the arrival pattern of the electrons on the screen looked like an interference pattern, and based on this, in order to explain this, it was necessary to invoke a wave, associate a wave with every electron. And what happened was, when this wave encountered the two slits, each slit now act like a secondary source, and if you wished to calculate the resultant wave at any point on the screen, it was the superposition of two contributions. So, what we found was that it was not possible to say that the electron arrives on the screen through either slit 1 or slit 2, and you have to admit the possibility that the electron basically goes through both the slits at the same time, because the wave corresponding to the electron passes through both the slits. So, the bottom line of all this discussion was that you have to give up the picture where you can think of these microscopic particles as particles which we are familiar with. Particles in the familiar world can be thought of when they move from one position to another. You can associate a trajectory with them. You write down the Newton's equations of motion and you can solve them, and finally at the end of the day you have the particle's position at every instant of time as it travels from one point to another. But we found that for microscopic particles like electrons, you have to think of it in terms of a wave propagation, and then as a consequence you have all the phenomena like interference, diffraction associated with waves also occurring for such particles. I also told you that this wave which you associate with the particle, you interpret as being the probability amplitude, the modulus square of this wave. So, this wave or the wave function psi, the mod square of this gives the probability density of finding the particle somewhere. This is what I told you in the last class. So, if you ask the question, what is the probability of finding the particle along the interval dx, in the interval dx centered at the point x on the screen, this will be given by the probability density into the interval dx, and the probability density can be calculated from the wave psi by taking its modulus and then squaring it. So, this psi is the probability amplitude and this is the probability density. The modulus square of it gives the probability density, whose interpretation we have discussed in the last class. Now, in today's lecture I am going to tell you the basic rules of quantum mechanics. The previous lectures have all been motivation and interpretation of the wave function, and motivation why we need to think of particles as in terms of waves. So, today we are going to go into the mechanics of these waves. So, this is what is called quantum mechanics or wave mechanics. And the first postulate of quantum mechanics, as I am going to present them to you, states that for every possible state of a particle, corresponding to every possible state of a particle, there is a different wave function psi associated with it. So, an electron, for example, could be in one of different possible states. It could be in many possible states, and at any given time it could be in one of them, and or there could be many possible states in which you may find the electron. So, for corresponding to each of these states, there is a different wave function psi. So, corresponding to every possible state of a microscopic particle, there is a wave function psi, and this wave function is governed by a wave equation known as the Schrodinger wave equation. So, let me also write down the Schrodinger wave equation. So, the Schrodinger wave equation is the wave equation governing the evolution of this psi. So, let me remind you once more, the first postulate is that corresponding to every state of your system, say you are dealing with an electron, so corresponding to every possible state of the electron, there is a different wave function psi, and the evolution of these wave functions is governed by the Schrodinger wave equation. And let me write down the Schrodinger wave equation. So, for a particle moving in, which can move in all three dimensions, the wave equation is I h cross del by del t psi. Now, psi could be a function of r and t. This is equal to minus h cross square by 2 m, where m is the mass of the particle. So, if it is an electron, it is the mass of the electron, Laplacian minus h cross square by 2 m Laplacian of psi plus v, which again could be a function of r and t into psi. So, this is the Schrodinger equation. So, this term over here is the partial derivative with respect to time. This term has spatial derivatives. The Laplacian, which we have already encountered earlier, has spatial derivatives in it. Now, when you have a particle under the influence of an external force, which is the situation quite often. For example, if you have an electron, the electron could be in an external potential under the influence of an external electric field. A static electric field could be represented in terms of a potential. So, if I have a uniform electric field, I am sure we all know that there is a corresponding electrostatic potential. So, any motion, any force, so when we do classical mechanics, the forces can be represented as gradients of potential under some conditions. So, this external force, action of the external force on the particle comes in here through the potential V. So, if I have a particle in an external potential, so then I have to also include this term. This term is the potential. The gradient of the potential minus the gradient of the potential gives me the force acting on the particle. So, when I am thinking of this, say a macroscopic particle, and I think of it in the usual classical picture, I would write down the equation of motion for a particle moving in an external potential, and for a macroscopic particle I would write down the equation. Let me just remind you what we are talking about. So, for a macroscopic particle, say a cricket ball or something like that, so if I had a macroscopic particle under the influence of an external force, then I would write down an equation which could be that the force, if the force could be represented in terms of a potential, if it were a potential force, then usually the force is minus the gradient of the potential. For potential forces, that is how you introduce the potential. So, then I would write down the equation of motion for the macroscopic particle in terms of the potential. M into the acceleration is the force, which is minus gradient of the potential, and I would solve this equation of motion, which would give me the trajectory of the particle, whereby I would know the position of the particle at every instant of time for this under the influence of this external force. Now, if you are dealing with microscopic particles, we have to abandon this picture where the particle moves in a trajectory, and we have to describe it in terms of a wave, and the evolution of the wave is going to be governed in the presence of the same potential. The evolution of the wave is now going to be governed by this wave equation, which tells me how the wave is going to evolve under the influence of that external force. Remember, the force is the minus the gradient of this potential. So, I have to now replace the trajectory. I can no longer think of the particle in terms of a trajectory. I have to think of it in terms of a wave, the evolution of the wave, and the mod square of this wave gives the probability amplitude. If I can calculate this wave at different positions, the modulus square of that gives me the probability amplitude. This is something which we have already discussed. The modulus square of the wave function tells me the probability amplitude. So, once I know the wave function, I can tell what is the probability of finding the particle somewhere. I cannot tell exactly where the particle is, like I can do for macroscopic particles, for which I can calculate trajectories. This has to be abandoned when we are dealing with microscopic particles, which we have to think in terms of waves, and the evolution of the wave is governed by this wave equation. So, this is the time derivative term which occurs in the wave equation. This has the spatial derivatives, and this is the term that arises due to any external influences, which we can represent through a potential. So, this is the Schrodinger wave equation. Now, we are going to restrict, in this course we are going to restrict our attention to particles which are free to move only in one dimension, along the x axis. So, this simplifies the discussion, that is all, but from this simplified discussion we can get a clear picture of what would happen if we were to deal with particles in 3 dimensions. It simplifies the mathematical analysis, that is why we are restricting our attention to particles which can move only in one direction along the x axis. So, under this simplification, the Laplacian now is just partial derivatives with respect to x, that is the only change which occurs. Psi is a function of x alone, and the potential V is also a function of just x. So, the equation now becomes I h cross del by del t psi, which is now a function of x and t, is equal to minus h cross by 2m partial derivative with respect to x, the second derivative with respect to x, plus v, which could now be a function of x and t, into psi. We will also make another simplifying assumption. We will assume that v is time independent. So, v is a function of x alone, that is, it is static, it is a static potential. So, for example, if I have a charged particle in an external electric field which is static, for example, a uniform electric field, we know the potential is proportional to the distance x, we have a static potential. But suppose I have a charged particle, let us say an electron bound in an atom, and we shine light on this atom. Now, we have discussed that light is essentially an oscillating electric and magnetic field. So, we have a time dependent external force, a time dependent external electric field. So, this is a situation that is not static. The analysis of such situations is more complicated. We are not going to deal with such situations in this course. We are going to deal with situations where the potential is static, it is just a function of x and it is not dependent on time. So, under such conditions we will now proceed to look for solutions under such conditions, and we are looking for solutions to this equation where x is v is now just a function of x, not of time. So, we are going to use the method of separation of variables, which is familiar. Remember, we have introduced this method when we were discussing standing waves, and what you do is we will take a trial solution of the form where psi x t is a function of is the product of two functions, capital X, which is a function of the position alone, and capital T, which is a function of time alone. So, we will take a trial solution like this. Recollect that this is the method of separation of variables. So, we are going to put a trial solution like this into our wave equation. Now, the partial derivative of this psi partial derivative with respect to time is going to act only on this function, and it is going to be now a total derivative. So, the equation, the Schrodinger equation in one dimension now reads as follows. So, I have to replace this with x into t, and the x will go out. I will have the time, the function of time left over here. So, what I have is I h cross x d by dt of capital T, that is the first term. Again, I replace this psi as a product of capital X and capital T. Capital T will now go outside because this is a derivative with respect to x, and what this gives me is this is equal to minus h cross square by 2m, capital T now comes out, d square dx square of capital X. And I will do the same replacement here, there is going to be no change, v, which is just a function of x now, into capital X into capital T. So, this is the Schrodinger equation with the separation of variables put in. Now, what we do, if you remember, we have to divide this equation, complete equation, by psi, which is x into t. So, when I divide this equation with x into t, if I divide this term with x into t, x cancels out, and what I have is I h cross, I am dividing it by x and t. So, 1 by t remains, d by dt of capital T. If I divide this by x into t, capital X into capital T, what I have is minus h cross square by 2m. I am dividing by capital X and capital T. So, capital T will cancel out, I will have a capital X left. This is, and this term will give me just v, which is a function of x alone. I am dividing by capital X and capital T. Now, notice that the left hand side is a function of time alone, the right hand side is a function of x alone. I am free to change time without changing x, I am free to change x without changing time. The fact that this equality must hold basically tells us that these two terms must be equal to a constant, and I am writing that constant as E. So, we have used the method of separation of variables, and it tells us that these two terms should separately be equal to a constant. We have to now solve these equations. Let us first look at the time part of this equation. So, the time part means that we have to look at this term, which is equal to a constant E. What this gives us is this differential equation I H cross is equal to T times E, where E is a constant, this capital T is a function of time. Now, the solution to this is easy to write down. The solution is T as a function of time, capital T as a function of time is equal to, there could be a constant which I am not writing down, an overall constant into e to the power minus I E T by H cross. And you can easily check that if you differentiate this once with respect to time, you will pull out a factor of minus I E by H cross. Minus I into plus I will give me 1. You have a 1 by H cross, will cancel out this H cross here, and I will get E. So, what this, if I differentiate this, I will get exactly the right hand side, and there could be an overall constant which I have not written down. So, this is the time part of the solution. Now, let me write down the spatial part of the solution. So, when dealing with the spatial part of the solution, it is convenient to introduce a constant another constant which is defined like this. So, we are going to introduce another constant p square, which is 2 m into E. So, we are going to introduce another constant p square, which is 2 m into E. We are now looking at the spatial part. Oh, before that, we are now going to focus our attention on a particular situation where we have a free particle. Let me first make this point. So, the first situation that we are going to consider is where we are dealing with a free particle. So, for a free particle, the potential V let me put this elsewhere, this need not come here. So, we are going to deal with a free particle and see what kind of solution this Schrodinger equation gives us. Remember, a free particle refers to a particle on which there is no external force. So, this kind of a particle has no potential, has no potential acting on it. So, this potential V is going to be set to 0. If I set the potential V to 0, the spatial part of this equation now becomes d square capital X dx square is equal to minus 2 m E by h cross square into x. Now, it is convenient to introduce a new variable, let me put it here. So, it is convenient to define a new variable. So, define this numerator 2 m E as a new variable p square equal to 2 m into E. So, with this new in terms of this new variable p, the equation governing capital X now becomes d square x dx square is equal to minus p square by h cross square into x. And this has two solutions. Basically, this we know that this is the simple harmonic oscillator equation, and the solution to this is quite straightforward to write down, and the solution is x as a function of x is a constant. Again, I could have a constant which I am not writing explicitly into e to the power plus minus I into p into x by h cross. If I differentiate this twice, I will pick up minus p square by h cross square, which is the equation that I have over here. So, it is very easy to check that this is just the simple harmonic oscillator equation, and it is quite straightforward to realize that this is the solution. There could be either plus here, plus p, or minus p, because we have to take the square root when we are dealing with that equation. So, this could be plus or minus, we can choose one of them and go ahead. So, combining this with the temporal solution, over here, what we find is that the resultant is psi x t can be written as some constant. I am now putting in the constant. Remember, both this and the temporal part had constants in front. I can take the product of those two constants and get another constant, e to the power minus I by h cross. So, I am writing the temporal part first. The time part is minus I e by h cross into t. So, which I have written as minus I by h cross e into t minus p into x, which is the spatial part. So, the spatial part has a solution which is given over here, plus minus I p x by h cross. I have taken only the plus, the solution with the plus sign, which is the one I have taken here. You could also have a solution with the minus sign, which will introduce a plus sign over here. So, bear in mind that there are two possibilities. I have just taken one of them over here. So, this is a solution of the Schrodinger equation for a free particle, where there could be an overall constant which is still undetermined. There is also an arbitrary constant E which appears, which I have not told you what it signifies, and there is another constant P which is related to E, which is not independent, but related to E as follows: P square is 2 m E. So, there is basically one constant, either you can think of it as either P or E, which I have to tell, and E, if I tell P, then E can be, E is fixed, therefore, if I fix E, then P is fixed, and there is an overall normalization constant over here. And these E and P are related as follows: E is equal to P square by 2 m. So, this is a solution of the Schrodinger wave equation, and the solution has an overall constant over here, and it has two constants over here which are not independent, which are related like this. So, I can fix any one of them and I can get the other constant. If I fix P, I will get E from that, and that is it. So, this is the solution of the Schrodinger equation. We have still not discussed the significance of this constant E, which appears when I integrate this equation, the Schrodinger equation, or the constant P, which appears when we integrate the Schrodinger differential equation. So, these are till now unknown constants whose significance I have not discussed. Now, if you remember de Broglie hypothesis, then you can straight away say what the significance of this E and P are, but we shall come back to the significance of this E and P in later on as we go along in this lecture, or possibly in the next lecture. Another point which I should make here, let us ask the question, what is the angular frequency of this wave? Now, you can straight away read the angular frequency of the wave if you think of this as e to the power minus I omega t. So, omega you see is E by h cross. If you ask what is the wave number of this wave, for this wave, the wave number, if you write this as e to the power I k x, then you can straight away read the fact that P by h cross is the wave number k. So, this solution of the Schrodinger equation has arbitrary constants which come about. There is only one of them that is independent in the exponent, there is only one of them which is independent, and it is this constant that also determines the angular frequency of the wave and the wave number for the wave. So, this is a plain pure sinusoidal wave solution for the Schrodinger wave equation. If I had chosen the minus sign, I would have, this is a wave propagating to the right. If I had chosen the minus sign, I would have got a wave propagating to the left. Now, the superposition of two such solutions is also a solution. Let me also write that down. So, I can have two different, you see this constant E is arbitrary, or in other words the constant P is arbitrary. Suppose I choose two different values for E and P, so I will refer to them as E1 P1 and E2 P2. Then I can E1 P1, the set of values E1 and P1 will give me a particular solution of the Schrodinger equation, which, as I have told you right in the start, corresponds to a particular state of the particle. If I choose a different set of values E2 and P2, I will get a different solution which corresponds to a different state of the particle, and I can now superpose these two solutions. That also is guaranteed to be a solution of the Schrodinger equation, because it is a linear equation. So, the superposition of two solutions is also a solution, and I can write down this superposition solution. So, let me write it down here. So, this psi is a superposition of two different solutions. This solution has the constants in this solution, the constants have value P1 and E1. The overall amplitude is A1. The amplitude, remember, could be complex. This solution, the constant has values P2 and E2, and there is an overall amplitude A2, which is again different from this. This corresponds to a particular state of the particle, in this case the electron, if you are dealing with an electron's wave function. This corresponds to a different state from this for the particle. The superposition of these two is again a different solution, so it corresponds to a third state of the particle. And if I change these coefficient constants, I will get different, each of them will give me a different state of the electron. I can generalize this further, so I can write down a solution that looks like this. So, here the constant P, which appears in our solution, can take any value in the range minus infinity to infinity. I am superposing all such values with different amplitudes. Here I have only two such values. I am superposing them with different amplitudes. So, corresponding to P1 there is a E1 and I have a particular amplitude for that wave. Corresponding to P2 there is an E2 which is the function of P2, and for that for this particular wave I have a different amplitude, and the superposition of this also gives me a solution. Now, what I am doing is I am superposing a sum of infinitely many momenta. So, I represent it as an integral. So, p will change, and when p changes, the particular wave, corresponding wave, is going to be added with a different amplitude. So, this amplitude also changes with p, and I am superposing all of these solutions to produce another solution, psi of x of t, psi which is a function of x and t. So, different set of amplitudes will give me different psi wave functions, and once I know psi, I can calculate the probability amplitude of finding the particle somewhere. So, if I ask the question, what happens if I make a measurement of the position of the particle, if I measure the particle's position, I know how to I can predict with the wave function. What I can predict with the wave function is as follows. If I know for a particular solution psi, the mod square of this gives the probability density rho x and the probability of finding the particle in an interval dx. So, if this is the region of space I am dealing with, this one dimensional, if I ask the question what is the probability of finding the particle in an interval dx around this point x, that is given, that probability can be calculated if I know the wave function, and it has the value rho x. So, rho x into the interval dx gives me the probability of finding the particle in this small interval around the point x. So, we know we can make some kind of a prediction of what we expect if I make the measurement of the position of the particle. What we can do with the wave function is that we can predict the probability of finding it at any position. So, once we know the wave function, we can tell what is the probability of finding the particle at different positions. But for a particle free to move in one dimension, position is not the only physical observable attribute that you can measure, physical observation that you can do. You can measure various other things. For example, you could measure the particle's momentum, or you could measure the particle's energy. For a particle which can move in 3 dimensions, all 3 dimensions, you can also talk about the particle's angular momentum. The question is, in quantum mechanics, where we represent the state of the particle as waves, how do we deal with other such observable quantities, physical observable quantities? How do we deal with a situation where I measure the momentum of the particle? So, I have represented the state of the particle by a wave. The question is, what will happen when I make a measurement of the momentum? So, here we have to introduce another postulate. So, I have already told you that the state of the particle is represented by a wave function psi. The second thing is the physical quantities, physical observable quantities are represented by Hermitian operators. So, corresponding to every physical observable quantity like position, momentum, energy, etc. for a particle, there is an operator, there is a Hermitian operator. So, we have now introduced 2 new words. I have to explain what they mean. The first thing is Hermitian and the second thing is operator, or you may say the other way around. I have introduced this Hermitian and operator. We are going to take up operators first, and then I am going to tell you what we mean by a Hermitian operator. So, an operator an operator which I will denote with a any symbol with a cap on top. So, this is the operator O with the cap. The fact that there is a cap on top or a hat on top is going to tell us that this is an operator, not a number. An operator is something that acts on a function to give me another function. So, let me give you the examples. An example of an operator is d by dx. So, the operator acting on the function, let us say sin kx is equal to d by dx of sin kx, which is equal to cos k into cos kx. So, what we see is that this operator acts on a function to give me another function. In this case, the function is sin kx. The function that I get when the operator O acts on this function, or the operator d by dx acts on this function, is k into cos kx. So, this is what is an operator. Let me give you another example of an operator. We have an operator O, I am using the same symbol, let us say, which is multiplication by 2. So, O acting on, let us say, x square, where O is defined as multiplication by 2. So, 2 times, this is 2 into x square. So, this is the operator here is multiplication by the number 2. So, when this operator acts on the function x square, it gives me 2 into x square. So, this is what we mean by an operator. An operator acts on a function to give me a different function. Now, there are situations where an operator acts on a function to give me a different function, but this different function, which is the resultant of the operator acting on psi, is the same old function psi multiplied by a number. If this is true, then this number is said to be an eigenvalue of the operator O, and this function psi is said to be an eigenfunction. So, an example of an eigenfunction and an eigenvalue is given below. I am going to give you one now. So, let us consider the operator d by dx, and this operator is going to act on e to the power I kx. This is going to give us I k into e to the power I kx. So, what we see is that the function e to the power I kx is an eigenfunction of this operator d by dx, and it has an eigenvalue I into k. Let me give you another example. The next example is when the same operator d by dx acts on sin kx, it gives me k into cos kx. We see that this is not an eigenfunction. So, sin kx is not an eigenfunction of d by dx, right, because when the operator d by dx acts on sin kx, it gives me a different function, which is not the same function. There is no way I can write this as the same function multiplied by a number. So, this is not an eigenfunction and it has no eigenvalue. Therefore, for this operator, similarly, this operator, this function is an eigenfunction of this operator, and it has an eigenvalue I into k. Now, I told you that what we that in quantum mechanics, corresponding to every physical observable, there is a Hermitian operator. So, what do we mean by a Hermitian operator? I have told you what we mean by an operator. I have also told you what we mean by the eigenvalue and the eigenfunction of an operator. Now, the the notion of a Hermitian operator is a little complicated. There is a definition which I shall not go into. As far as we are concerned, we are mainly interested in one property of Hermitian operators, and I am going to just tell you about this property. So, Hermitian operators are operators all of whose eigenvalues are real. So, Hermitian operators are a particular type of operators which have this special feature that its eigenvalues are all real. So, operators can have typically more than one, can have many eigenvalues. For example, the operator d by dx, which I have introduced as an example, d by dx, has many eigenvalues. The function e to the power I k x is an eigenfunction for any value of k. This is an eigenfunction. So, for each value of k, I will have a different eigenvalue I into k. So, if k is 1, there will be a particular eigenvalue I. If k is 2, the eigenvalue is 2i. If k is 3, the eigenvalue is 3i. Any value of k is an eigenvalue, is a different eigenvalue of this operator. So, operators typically have many eigenvalues, many and correspondingly many eigenfunctions. Now, Hermitian operators are a special class of operators, all of whose eigenvalues are real. And it is the postulate of quantum mechanics that corresponding to every physical observable, there is a Hermitian operator associated with it. So, let me give you an example of a Hermitian operator. The operator, so let me give you an example. So, let us consider the operator I d by dx, and let us look at the function e to the power, let us I k x, let us consider instead minus I d by dx. So, let us look at the function e to the power I k x, and when this operator acts on this, it gives us, what does it give us? So, if I differentiate this with x, I will pick up a sign of a factor of I into k, and I will retain the original function. I into minus I gives 1. So, I have a k. So, this gives me k into e to the power I k x. So, what we see is that this operator O, defined as minus I d by dx, this is Hermitian because its eigenvalues are all real, and you can check that it has no imaginary eigenvalues. Eigenvalues are all real. I could also give you an example of an operator. Let us look at this operator d by dx. So, d by dx acting on I k x gives me I k into e to the power I k x. Now, notice that this e to the power I k x is an eigenfunction of this operator and it has an imaginary eigenvalue. Such an operator is not Hermitian. So, I have given you an example of a Hermitian operator. I have also given you an example of an operator that is not Hermitian, and in quantum mechanics corresponding to every physical observable there is a Hermitian operator. Let me give you an example examples. So, for a particle moving in one dimension, we have what are the physical observables that you can think of. The position, the corresponding to the position, we have a position operator x, which is defined as follows: when x acts on a function psi x, it gives me the variable x into psi x. So, the function psi x is not an eigenfunction of this operator x, because x acting on psi x, the operator x acting on psi x is the variable x into psi x. If you change x, this is not a constant. If you change x, the value of this variable also changes. So, this is not an eigenfunction of this operator, and corresponding to position we have this operator x, which is defined like this. Corresponding to momentum, we have the momentum operator p, which is minus I h cross del by del x. So, this is the momentum operator, and the other quantity which you can measure for a particle, observable quantity for a particle free to move in one dimension, is the energy. Now, the operator corresponding to energy, or more strictly speaking, there is an operator corresponding to the Hamiltonian, which as far as we are concerned in this course is the energy, and we shall denote this by h, and this is I h cross del by del t, I h cross del by del t. So, what we see that we have to postulate two things, two postulates that we have encountered of quantum mechanics. The first postulate, the first assumption is that associated with every state of the particle there is a different wave function, and these wave functions are governed by the Schrodinger equation. I have told you what the Schrodinger equation is. Associated with every physical variable which you can measure, every physical observable quantity of the attribute of the particle that you can measure. For example, for a particle in 3 dimensions, in moving only in a single dimension, you have its position, momentum and energy. Corresponding to the position there is a position operator, corresponding to momentum there is a momentum operator, corresponding to energy, or strictly speaking the Hamiltonian, there is a Hamiltonian operator, which is given over here, I h cross del by del t. The momentum operator is minus I h cross del by del x. So, corresponding to every physical quantity there is an operator. In the next lecture I shall tell you what happens when we make the measurement, what is the physical interpretation, I mean what role do these operators play, that I shall discuss in the next class. There is a point which I should make before I close today's lecture. In today's lecture we worked out the solution corresponding of the Schrodinger equation corresponding to a free particle, and in this solution I told you that there is this constant E which comes up when I solve this equation. There is this constant E which comes up, and related to E there is a constant P which is related to E like this. So, P is essentially the square root of 2m into E with the plus or minus sign possible, right. Now, the point which I forgot to tell you is that the constant E has to necessarily be positive, it cannot be negative, and the reason for this is as follows. The constant E is related to the constant P over here. So, P is equal to plus minus 2 m E, and till now in our discussion E and P are both arbitrary constants which are related to one another, and they essentially fix the dispersion relation for the wave. Now, E has to be real and positive, because if E is negative, the constant P becomes imaginary. If I have an imaginary constant over here and I multiply it with I, then the x dependence now becomes of the form e to the power some real constant into x. Let me make this point clear. Why does E have to be necessarily positive? If E is negative, then P becomes imaginary, and if I have e to the power minus I plus I p x, that is the x dependence. If this P is imaginary, let us say P is I alpha, then this becomes minus alpha x, because I and I give minus 1, and the range of x is from minus infinity to plus infinity. Now, notice if the x dependence of the wave function is of this form, it blows up when x goes to minus infinity. The wave function should not blow up, because the wave function gives the probability, and the modulus square of the wave function integrated should be 1. So, if you want this to be satisfied, the wave function should not blow up, which basically tells us that P cannot be imaginary, and if P cannot be imaginary, E has to be real. So, in this arbitrary solution, in this solution that we have worked out, E could be arbitrary, an arbitrary constant, as long as it is real. That is a point which I had forgotten to mention. So, let me bring today's lecture to an end over here. We shall resume our discussion of how to interpret these operators, how to manipulate with them in the next lecture.